All right. So as I said, it's already broken the dy dx down in this quiz problem, right? So we want to get the, why am I echoing? Somebody mute if they're not muted. That might be the problem. Okay. So we want to get all the y's on one side, all the x's on the other. So because dy is on the left, I am going to go ahead and what happened? Apparently somehow I closed my window. Fantastic. Yet it's still right there. Yay for technology. All right, can you guys see the quiz? Okay. So dy's on the left. I'm going to move my dy's to that side, or my y's. So this y would have to go over here, and it would have to be divided on that side. On the other side, I have x dx, and I would need to divide by this whole term, x squared plus 1. I could then integrate both sides because they are separated. The left-hand side is the natural log of y. The right-hand side, if we do a u substitution, if you didn't see it right off the bat, looks like this. And that means we're missing a 2 inside and a 1/2 outside. So that becomes 1/2 integral du over u, or 1/2 natural log of u plus a constant. Replacing u, we have that. So that would be your general if you wanted to stop there. We can use that to get c because we've got an initial condition. It says that when x is 0, y is equal to -2. And if you forgot the absolute values when you integrated, this should have thrown up a red flag for you because you would have had the log of a negative number, and you're not allowed to have that. So the absolute values are important in this problem. So you'd have natural log of 2 then, 1/2, this would be natural log. If x is 0, 0 squared plus 1 is just going to be 1. And the natural log of 1 we all love because it goes to 0. So you end up with c is the natural log of 2. So then you go back and you say, okay, I'm going to plug that in now. No, you're not okay with this? You're shaking your head, Jay.
Because that's exactly what I did, and then I erased it all and wrote something else.
Okay. And if you want to get y by itself, I think the best course of action would probably be, we want to get a 1/2 in front of this guy. So I'm thinking maybe we put a 2 over 2 in front. And then we split that apart so that the 2 in the numerator goes up as a power. And we leave the 1/2. So basically it would look like this. And the reason I did that is because then they both have a 1/2 in front. I could put them together. I mean, I could have put them together before, but I can leave the 1/2 out front now. The other way you could do it, if you don't like that, is just leave it this way and take this 1/2 up as a power. So this would be natural log of the square root plus natural log 2. And the natural log plus natural log is the multiplication of the insides. And yes, Daniel, now that you've got log and log on both sides, you can raise both sides E.
No, I did that much earlier. So I did that right after the general
So up
answer.
here,
So yeah, scroll up a wee bit.
you could do that.
But I got -2 for C instead of ln2.
Is that because you didn't have the absolute values?
Well, no, because I had the absolute values, but then I got rid of the ln, which would have removed the absolute values. So my general answer would have been y equals the square root of x squared plus 1 times c.
I did the same thing.
So you're saying here you raised E.
Yes. So I raised e. Actually, no, go up a little bit more.
Well, before you plugged in, yeah. So right here.
I mean, yeah. So then y.
Okay, so this would be absolute value y is equal to.
Okay, so I forgot the absolute value. I didn't know that.
You'd have to move this 1/2 up because this E and log can't cancel yet. So that 1/2 would have to go up as a power.
Mhm.
So you would end up with you get C times the square root of x squared plus 1 out of that.
Okay, so for future reference, when you're using E,
And that's exactly what I'm going to get down here, right?
So even since I removed the ln by substituting E, y would still be absolute value. You still got to keep the absolute value.
Well, yeah, if you haven't plugged in the numbers yet, you got to be careful. So this
Okay, because what I did was,
that as well.
in order to solve for C, I did -2 equals under the square root is 0 squared plus 1 times C.
Right.
And then
I see what happened.
Yeah.
But that would just give you the wrong sign because you dropped the absolutes.
Correct.
Yeah, should be this guy, I believe.
Close enough, but it's -2. All right. Thank you for going over it.
Not a problem. All right. So let's go ahead and get started with the material for today, unless you have any other questions. All right, so I'll take that as a no. All right. So we changed gears a little bit. We went from direct applications to differential equations, which is still an application of integration, but it's a little different in that we have to use integrals and derivatives almost simultaneously. And it's certainly a different type of equation or problem than we're used to. So we took care of what's called the separable equations yesterday. We are now going to look at linear differential equations. And those are of this form. So I want you to memorize this form. You might also see y prime instead of dy dx. Then there's some function of x times y equals some q of x. The problem has to be in this form in order to use this method. So one of the mistakes I see often is you have to put the problem into the correct form. The person will solve for this integrating factor that we'll talk about in a second, but then they'll plug it back into the original equation, which causes problems. So somebody solved this type of differential equation a long, long time ago and found this guy called the integrating factor. And the integrating factor is of the form e to an integral. And I will often call this thing mu. It's a Greek symbol. So it's e to the integral of whatever that p of x function is, dx. And of course, if it's, if the equation could be dy dt, or we'll see something like di dt later. Okay, so it doesn't have to be x's and y's all the time, but it does have to be in that format. Another thing you'll hear me say quite often is the variable of which the differential equation is over. That means, what is this variable? It's basically, what variable is there a derivative of within the problem? So I think instead of solving for the integrating factor, which is what the majority of texts will do, I think I'm just going to go ahead and jump into a problem and work out the steps. Is there anyone opposed to starting that way? All right. So let's look at this first problem and go through the form. I've got x times y prime minus y equals 3x. Now, I just got done telling you before that it's got to be in this format. So notice the dy dx, or the y prime, is by itself. But in the problem we're given, it isn't. So the very first thing we should do is get y prime by itself. So to do that, I'm going to divide through by x. And that leaves me with y prime. And I'm going to write it specifically this way: 1 over x times y equals 3. Now, why did I write it that way? Well, the format we want is y prime plus some function of x times y equals some function of x, q. So p of x can easily be seen in the problem. Now, another thing that you have to be careful of is the format is plus. And in our problem, it is minus. So we need to take that negative as part of our p of x. So I'm going to go as far as to write it as plus negative 1 over x. So our first thing is to identify p of x, and that is negative 1 over x. Once you have that, you can find the integrating factor. Okay, so step 1 is get it in the correct format. Step 2, identify p of x and calculate the integrating factor. So the integrating factor is mu, and that is e to the integral of 1 over x, negative 1 over x, dx. Hopefully you see that that is the natural log. And again, another thing I see often is you've got e to the log here. People will just cancel them. But because of that minus sign, we're not allowed. So we have to think of that as a -1 out in front. And we need to pull it up here as a power. And once we've done that, now the e and the log cancel. And this is just going to become 1 over x. Right? If we have x to the -1 power, that's the same thing as 1 over x. All right. So what do we do with that? Well, the next step is to take the integrating factor and multiply it by the original equation in the correct form. So that was this right here. This is the equation in the correct form. I'm going to take that and multiply everything there by 1 over x. So 1 over x, y prime, minus, now there's 1 over x, I'm going to multiply it by a 1 over x, that's going to become 1 over x squared times y. And on the right-hand side, I'm going to get 3 over x. Everyone with me so far?
Yes.
Okay. Thank you. All right. So now I am going to do some magic and then I'll explain it. I call it mathemagic. If we look at the left-hand side here, I'm going to claim to you that this is the derivative of y times the integrating factor. So what did I just do? Well, effectively, I used the product rule in reverse. So let's prove it. And this is a good point in the problem to show that you've done it correctly. If you have found the incorrect integrating factor and these two things are not equal, then you've done something wrong, right? It'll tell you to go back and fix it. So this step should always turn out to be the derivative with respect to x of the variable that the equation is over, y in this case, multiplied by the integrating factor. So as I said, let's check it. So derivative of y with respect to x, well, that's just called y prime. Leave the 1 over x alone. Leave y alone. What's the derivative of 1 over x with respect to x?
-x to the -2.
Right, which is the same thing as saying minus 1 over x squared, right?
Yes.
Is that the same thing that I have in part 3?
Yes.
All right, so that does work then. So what I claimed was true. And that also means that we found the integrating factor correctly. And I'm going to leave the right-hand side alone. Now here's where the problem gets fun, if it wasn't already fun for you yet. I'm going to take this d over dx, and I'm going to break it apart, and I'm going to move the dx to the right-hand side. And once I've done that, I now have a differential on both sides. So I'm going to go ahead and integrate. Does anyone have an idea of what we're going to get on the left-hand side?
Just y times 1 over x.
Correct. That is the integral of a differential. All right, so you might recall way back when I did this for you, and I told you that my professor did it for me, and it made me remember forever. This is the same thing, right? This is d of y times 1 over x. So when I integrate, I just get what's inside the brackets. And that's the case every single time you do one of these problems. So once you get to this point, the left-hand side is always going to just become whatever's in the bracket. Right-hand side, I have to solve. It's easy though. This is dx over x, which we should recognize as the natural log. And we have plus c. So I just want to solve for y, and then we need to find, actually, I guess we could leave it where it is to find c first. Right, c is going to be y over x minus 3 log x. We've got this initial condition right here. So when x is 2, y is 8 log 2. So 8 log 2 over 2 minus 3 log 2. So that's going to be 4 log 2 minus 3 log 2, or log 2 for C. Which means if I come back up here now, we could simply just multiply by x on the other side, but let's see what happens if we put these two things together first. This would be the natural log of 2x cubed. I bring this up as a power, and then it's the addition of 2 logs, so you'd multiply the insides. And then you would multiply the other side by x. So all said and done, you would get y equals x natural log 2x cubed. So let me just go back through the steps one more time. First step was to take the original equation and get it in the correct format. So we needed y prime by itself. We did that. We established p of x, which was minus 1 over x. From that, we calculated the integrating factor, mu. Once we have mu, we multiply through the equation in the correct format. And if we did that correctly, then the left-hand side should collapse down to the derivative of the integrating factor times y in this case. We then moved dx to the right-hand side and integrated both sides. And then after that, it's standard procedure. It's solve for c, get your particular solution. You guys need me to leave that there for a second? So let me see how many of these there are. There's 4. And then applications. Okay. So I think maybe I'll do 1 to 2 more of these. I want to let you guys get your hands on them. But I know that you definitely need to see at least one more. Guess let's try D here. So again, the first thing I have to do is get it in the correct format. So I need y prime by itself, which means I need to divide through by cosine here. So y prime plus, this is going to be y times sine over cosine equals 1 over cosine. But sine over cosine can be written as tangent. And 1 over cosine is secant. So I'm going to write it that way. So this is in the correct format, which is y prime plus p of x y must equal some q of x. That means that p of x must equal tangent in this case. So to find the integrating factor, I need to integrate tangent. Anybody remember that off the top of their head?
Is it secant squared?
That's the derivative of tan, but it still involves a secant.
Sec x, tan x.
That's derivative of secant. It's natural log of the secant. And that's really nice because E and log cancel. So we just get secant out of that.
I just had a quick question. When you do e to the integral of, why don't you have to worry about like a plus c?
Remember later on in the problem, you integrate again.
Mm-hmm.
So if you had a constant there.
Oh, okay.
it's technically, yes, there should be a plus C, but I'm pretty sure somewhere along the way it gets taken care of.
That makes sense. Okay.
All right, so where was I? We got mu, the integrating factor, which is secant. You always take that guy and multiply by the equation in the correct form. Which looks like that. And then I claimed to you that the left-hand side should always collapse down to the derivative of y times the integrating factor. So let's see if that makes sense. So derivative of y with respect to x, leave the secant alone. That gives us y prime secant x. That's our first term. If I leave y alone, the derivative of secant is secant tan. So it looks like our left-hand side is good, which means we can go ahead and put our right-hand side down here. Then we split up the d over dx and integrate. Right, so all I
Okay,
did,
real quick. I'm still a little confused, like, so from 3 to 4, how are we getting from 3 to 4? I'm sorry, I'm like lost there.
so the left-hand side is always going to be the derivative with respect to the variable being used, in this case x, of whatever the differential equation is over, which is y, because we have y prime, and the integrating factor. So it's always going to be y times mu, or if it was some other variable times mu, whatever the differential equation is over. And then I just expand it to prove that it still works. Right, so basically I go backwards. And then once you're there, you can take this dx and move it to the other side, which is my next step here. And once you do that, you integrate. The left-hand side's great. It always is lovely because it just comes out as whatever's inside those brackets. And then the right-hand side, what's the integral of secant squared?
Tangent.
So it's tan. We okay with that?
Yes.
Okay. So were we given a condition? Yes. So when x is pi, y is square root of pi over 3. So square root of pi over 3 secant of pi equals tan pi plus c. So what is secant pi and what is tangent pi?
Secant pi is another way of saying 1 over cosine pi, which
Mhm.
is 1 over -1, which is -1.
Right? And same thing with tan, right? Tan is sine over cosine. Sine of pi is 0.
Mhm.
So 0. So this gives us that C is negative root pi over 3. So the last thing I would do is divide through by secant to get y equals. So see, tan is sine over cosine. If I divide by secant, that's like multiplying by cosine, right? So this is sine over cosine. And then dividing by secant is multiplying by cosine. And then this one, same thing. I'm going to multiply by cosine. So all said and done with that problem. It's like that. Good, bad, no clue. How are we feeling so far?
Great.
Why did you multiply by the cosine again? So like you multiplied this, or you did the secant, brought it to the other side, but can you just explain how you got there?
Say that one more time, sorry.
Can you explain the last 2 steps?
So how did I get from to there and then there?
No, just the first one. But yeah.
So I divided through by secant everywhere, right? And dividing by secant is the same thing as multiplying by cosine.
Okay, thank you.
And then the other thing was I turned tan into sine over cosine. And you're welcome. Would you guys like me to do at least one more of these? Or try the last 2 here?
I just have a question. Like, I'm fine trying them, but on B, would the function of x in the form just be 1? Because there's no x term?
It would be -1.
Yeah, because of the, okay. But it would just be -1 because there's no x there.
Yeah.
Alright. Then, yeah,
When we say a function of x, there's no reason that can't be a constant.
alright, I was just clarifying. Thank you.
So what we have left are these 2 problems in this section, and then we have applications. So in the applications, we have orthogonal trajectories. Those are going to generally be separation of variables. Then we have electrical circuits. That's going to be what we're doing today. I'll most likely skip the mixing problems because they're just too confusing for people half the time. And then there's Newton's law of cooling, which is a combination of both. So it's a good review problem of both types. So my question is, would you like me to do another one of these and continue? Let you try them and then move on to the applications. How are you guys feeling?
I would rather do them myself.
Okay, how about the rest of the group?
Yeah, I wouldn't mind trying one or two.
Okay. So do you
Yeah,
guys
if we can do them now and then move on, that would be good. So we kind of like burn it into our brain how to do it.
So let's try maybe 20 minutes. See if we can do these two. Do you guys need me to put the problems back up? No?
Yeah,
Oh, all right, hold on.
just really basic.
There you go. Okay. So I will pause. So I'm going to go ahead and resume recording. So, as I said, that this is a direct application, and I just wanted to give you a little bit of background quickly. So this equation up here comes from a set of rules made by this guy named Kirchhoff. I think that's how you spell his name, if I remember correctly. It's been quite some time. But there are these laws, they're called Kirchhoff's laws or rules. And they basically say that if you're dealing with any kind of electrical circuit, that in any particular loop within that circuit, so a closed loop, so basically if you start with a power source on one end and you come back to the other side of the power source, the total voltage from one side to the other has to equal the voltage of the battery. And this circuit that's given to us in the problem looks something like, let's see, it's got an inductor, and then it's got a resistor, and then a battery. So this is the battery. This is called an inductor. Basically just a coil of wire. And this is our resistor. So what this equation says, and note that E here is voltage. And the reason for that is because voltage uses the unit volts, which is represented by a V. So it's problematic to call it V of T with units of V. So instead, in this problem, they use E. You might also see this in an electrical engineering or physics class. So that's phi or potential. So you got this battery here that's got some voltage. You've got an inductor, which is in henries. And the inductors represented by an L. Again, because we already have I for current. and resistor is represented by R. So we put E here. Now, notice it does say E of T. So in the real world, as we always say, right, voltage deteriorates over time. So if you have a battery, right, that doesn't last forever. But if you do have a power source like a wall outlet, then that thing can be constant, right? So the problem here, so if we go around the loop, each one of these things is called a voltage drop. So the voltage drop across the inductor is di dt times L. The voltage drop across the resistor is its current times its resistance. And those two things have to add up to the total voltage of the battery. So that's just some background. I don't require you to recite any of those things, but that's, you know, where this equation comes from. So the things that we're given are the resistance in units of ohms, the inductance, which is going to be in units of henries, and the voltage, which is going to be units of volts. So let's look at the problem here. Also notice, before I do that, notice it says the differential equation is a function of I of t. So instead of y, we're now using I. And instead of x, we're now using t. Okay. So the problem says, simple circuit, as pictured above, has a resistance of 12 ohms. So R is 12. The inductance, L, is 4. And we're given a battery with a constant voltage, which is 60. Then it says the switch is closed when t equals 0. So let's come back to that. They ask us, find I of t, and then the current after 1 second. Well, we're just going to use the equation given to us here. Right? We're not asked to start with the circuit, build this equation. We're given the equation. And we just need to plug in L, R, and E. So this is going to be 4 di dt plus 12I equals 60, just by substituting. And we know from the problems that we just did that we always want to get the derivative by itself. So I need to divide through by 4 to start the problem. So then I'm going to have di dt, 3I, and 15. Okay, so the only thing special I've done so far is just use some new variables. Now, this is in the correct format because I have my derivative plus some function times I equals some other function. So P of X, or in this case, P of T, is 3. Right, because this is I prime plus P of T I equals Q of T. So if we have P of T, we can find the integrating factor. Again, this time dt instead of dx. It's important that you keep with the correct variables. So it looks like I get e to the 3t out of that. Next step is to take that and multiply it by the equation in the correct form. So this side I'm going to claim is going to be d dt of the integrating factor times the function the differential equation is over, which in this case is I. So let's prove that to ourselves. So let's differentiate I first. That would give us di dt, and we would leave e to the 3t alone. That's our first term, so that looks good. Then leave I alone. The derivative of e to the 3t is 3e to the 3t. So that term looks good. So it appears everything is fine so far, which means we can now break up that differential or that derivative and integrate. So again, the left-hand side is glorious. It's just going to be e to the 3t times I. Right-hand side, now I would use a u substitution here. Which means I need a 3 inside, and I would divide by a 3 on the outside. Or in this case, I'm going to break 15 into 5 times 3. And I'll leave the 3 inside, pull the 5 outside. And that'll take care of my problem. Either way that you prefer to do it works. So it'd be 5 integral e to the u du which should look like that. So I've got e to the 3t I equals 5e to the 3t plus c. Here's where, so this could be my general if I wanted to call it that. I go back up and remember it says the switch is closed when t equals 0. What does that mean?
There's no voltage when t equals 0.
So no voltage, which means no what else?
Current.
There's no current. So I of 0 is 0. That's what that tells us. Right, so they're saying that there's some switch here. If I drew it with a switch, that switch doesn't close until t equals 0. And therefore there's no current flow at that immediate time. So e to the 3 times 0 equals 0. Right, so everywhere I see t, I plug in 0. Everywhere I see I plug in 0. This side becomes 0. E to the 0 is 1, so this becomes 5. And so that tells me that e equals -5. The last step is to get I by itself, so divide through by e to the 3t. So cancel here and here. And instead of leaving it in the denominator, I'm going to pull it up to the numerator. And the last thing I want to do is factor out that 5. The reason for that is because I want you to see what this thing looks like. So you should be able to, in your head, get an idea of what that function looks like, just because of the form I put it in. But let's go ahead and plot it and just see if what we see makes sense. That equation there is the equation of the current for any time t. Just putting the function in here. Okay. Let's just let me share this screen with you. So here's what that curve looks like. So at t equals 0, the switch turns on, right? And we build up current. And it looks like around 2 seconds, we're starting to level off, right? Let's go out to maybe 5. So now you can see getting pretty good, right? Looks pretty level. I can go all the way out to maybe 100 seconds, right? Still very, very level. And it's at 5. So does that make sense? So looking at the equation, what's the limit of that function?
Five.
Right, the e to the minus 3t, as t gets really big, goes to 0, right? So I equals 5. So as time grows, this thing just turns out to be 5. So this equation is really only important for the first couple seconds, and then it's just 5. Now it does say here, find I of t and then find the current after 1 second. So we would just need to do I of 1. And let's see what that is. And that keeps going. But it's already at 4.75 something after just 1 second. So it ramps up pretty quickly, right? It's exponential. Now, of course, this is because the voltage is constant, right? We also know that there's things like alternating current, things like that. We can alternate voltage. We could make the voltage something that's dependent on time because it's going to decrease over time. Right, so there's plenty of ways to make this both more interesting and apply to more functions.
Okay, so maybe a stupid question. So for that last part where it wants us to find the current after 1 second,
Mhm.
do we just plug in 1 for t? Like, how do we do that?
Yeah, sorry, I realized after I did it that I was still sharing the other screen. Here's the
Okay,
plugged it in.
that's what I thought, but I wasn't 100% sure.
Yep, that's it. So I think the quiz problem is something like this one. And again, the if the voltage isn't constant, well, that just means that the right-hand side of your equation is going to be a more difficult integral, right? So as I said, I'm going to skip the mixing problem for now. I want to get to Newton's law of cooling. I want to do an example. I'm going to let you guys try one. Because again, this is also closely related to what we're doing today. However, I am going to solve this using both methods. Because I think it's a good idea to be able to do things differently. Not everybody thinks the exact same way. So this is a pretty interesting concept, Newton's law of cooling. I had actually never heard of it until I started teaching differential equations, believe it or not. Especially being that my background is in physics. So this example here is kind of boring. It's about a cake that gets taken out of the oven and it asks, when's it okay to scarf it down? When I teach differential equations, I found a problem in the text that I thought was interesting. It's a CSI type problem. And it literally is, you found a body, it's this temperature, it was this temperature outside. How long has the person been deceased? So the idea of the problem is that you're given an object at some temperature, you place it into a room or an environment that is some other temperature. What is the temperature of the object after being placed in that environment for a certain amount of time? And the formula for that is this equation right here. And forgive me that temperature and time are both T. So I'm going to say big T and little t a lot. So the derivative of temperature with respect to time is equal to a constant of proportionality, K, times the quantity of the temperature T, big T, minus the temperature around the object called T sub m. So what I would like to do is I'm going to solve this differential equation without any numbers. And then once I've done that, I'm going to use my equation with the numbers given in example 1 to solve it. However, if I give you one of these problems, I don't want you to just take my result and plug in numbers, right? That doesn't show me that you know anything. That just shows me you can plug numbers in. I would like to see you be able to solve the differential equation first. So let me start with that differential. So I've got the derivative of big T with respect to little t equals K times T minus Tm. So let's do this using linear differential equations, since that's most fresh in our minds. I am going to multiply through by k here, and this will give me kt minus ktm. Now, if I want to get it into the correct format, I need my derivative and this k times temperature to be on the same side. So I'm going to subtract this back over to the other side.
Why do you choose that KT versus the KT of the object, or like the temperature surrounding the?
So the differential equation is a differential equation of temperature T, big T. T sub m is a constant.
That makes sense. Thank you.
Mm-hmm. So of course you could, I mean, I guess you could make the temperature Tm a variable, but that would completely change the problem. All right, so let's start at this point now. I've got it in the right format, right? This is T prime minus KT equals some function of temperature, or little time t. So P of t here is negative k. Is that clear to everybody? I'm going to assume that's a yes since no one made any comments. So again, remember this should be plus some P of t. And then over here we'd have some Q of t. So P of t is minus k, which means my integrating factor is e to the integral of minus k dt. And that just gives me minus kt. So then I take that guy and I multiply him by everything that I started with up here. And I purposely write it this way because I know that I'm going to check myself by taking the derivative. So this side better be the derivative with respect to t, time, of the integrating factor times the variable which the differential equation is over, which is big T temperature. So again, check yourself. So derivative of temperature with respect to time is dt d little t, and we leave the e to the minus kt alone. That's our first term. If we were to differentiate the exponential, we would get a minus k down in front. And then the exponential again, e to the minus kt times temperature. And then of course the right-hand side stays the way it is. So everything checks out there. Break off. The computer's ready to start having some fits. Break off the dt here I'm just going to come over to the left side now to give myself some room. And integrate. The left-hand side is always great. Come on, computer, hang in there, man. It's just going to give back what's inside the brackets. Right-hand side, now Tm is a constant. And if I were to say, let u equal minus kt, du would be minus k dt, which is great because we have that there. So that'd be the integral of e to the u du, or just e to the u plus a constant. That's fine. We can leave it like this. Tm, this would be e to the minus kt plus c. And if I really wanted, I could multiply through by Tm. And all that's going to do is just make this, come on, erase. You can just call that C1, right? Because Tm is a constant, C was a constant. If I multiply them, it's a new constant. Last thing.
What is the du? I'm sorry. Is that a k or what is
Yeah,
that?
it's minus k, sorry.
Oh, okay. Sorry.
Is that better? I don't know if it's any better.
Yeah, yeah. It kind of looked like an LE to me. So
All right, so the last thing I want to do is get big T temperature by itself. So divide through by e to the minus kt. If I divided C1 by e to the minus kt, that's the same thing as multiplying by e to the kt. That right there is my solution. Temperature that is a function of time given some temperature of the surroundings and the constant of proportionality. Let me go ahead and solve it again quickly using the method that we learned last time so that you can decide which one you like best. I personally like this method better, but I think you got to be a little bit better at algebra to do this one. So T minus Tm, that's all a function of temperature because Tm is a constant. So I am going to divide this side by T minus Tm and multiply this side by dt. That allows me to integrate because that's a separable differential equation, right? It's all big T temperature on the left, all little t time on the right. Because again, K is just a constant on that side. This on the left is going to give me natural log of T minus Tm. And we've seen that many times with partial fractions, right? This is just T minus some number. It's still going to give me back natural log. On the right-hand side, we get KT plus a constant. If we want to get T temperature outside of that log, I have to raise both sides E. So the left-hand side would be T minus Tm. Right-hand side would be E to the KT. And notice we've got plus C, which we've done before. We say we can make that times E to the C. Or let's just call that C1. Why did I do that? Well, now when I move the Tm to the other side, notice I get the exact same equation that I got last time. All right. So I really like that problem because, one, there's no numbers. It's all variables and constants. It's all letters, let's say. And you can really prove that you know how to do both types of differential equation using the same problem. So all that being said and done, we can now actually solve this problem here, which I know you've all been dying to know the answer. So it says when a cake is removed from an oven and placed into a room with temperature 70 degrees Fahrenheit, its temperature is initially known to be 300. So the cake is 300. The room that it's placed into is 70. After 3 minutes, the cake's temperature is 200 degrees. Find a function for the temperature at any time t that finds the temperature after removal from the oven. Estimate how long it would take until the cake could safely be eaten. Well, that's all arbitrary, so we'll come up with a way for that part. It should be a little more defined in terms of that part of the question. But let's go ahead and do the first part. So what all did they give us? Well, they told us that T sub m is 70, right? They said the room is 70 degrees. Then they said the initial temperature of the cake is 300. So the temperature at little t equals 0 is 300 degrees. And then it says 3 minutes later, the temperature is now 200. So the temperature at 3 minutes is 200 degrees. So now we need to use those three facts and this equation that we came up with. So we're told that Tm is 70. Then it tells us that when little t is 0, okay, so that the temperature is 300. So 300 equals 70 plus C1 e to the k times 0. And there is a reason that I used the 0 term first, because it will notice that the equation I have here has C1 and K. Those are two unknowns. And I'm given two conditions. This condition alone will eliminate K and allow me to solve for C. So typically if you have one that's got 0 in it, it's probably best to use it first. So let's see, this would be 230 equals C1. Now e to the 0 is just 1, right? So right off the bat, we get C1 is 230. So now we have that T of T is 70 plus 230 e to the kt. Okay. So now we need to solve for k. So use the other condition. That was temperature at 3 minutes is 200. So now 200 equals 70 plus 230 e to the k times 3. So you would subtract 70 and divide by 230. Then take natural log of both sides. And then finally divide through by 3, right? So k equals 1/3 natural log of 13 over 23. And in this particular case, I am okay if you use a decimal. So 1/3 times natural log 13 over 23. So I'm just going to stop at, say, 1902, or round up. So 4 decimal places. Let's go with that. So once you have k, you plug it back in. That is your equation for any time t. Now the last part of the problem said, what time is it okay to eat? Well, let's just assume that the majority of us are happy to eat cake at 90 degrees Fahrenheit. So now the question is, can you solve for little t when big T is 90? And I'm assuming that that's not a trouble for you to solve that. Not necessarily the manner that I did, but I don't believe that you have any trouble getting T out of that. So I just went ahead and did that quickly so we can get a number. Because I want to leave as much time for you guys to try some of these as possible. So natural log 2 over 23. I get 12.8. I did that correctly. Seems a little long. I'm gonna double check myself.
Sounds right. You're supposed to let the cake cool before you ice it anyway, you know.
Yeah, double checking it says 12.8409. So yeah. So it takes about 12 minutes for that cake to go from 300 degrees to 90 degrees. Just stay put there. Darn it. Stop moving. There we go. Okay. Whew. Long problem. What I would like you guys to do is go ahead and try the second one here. And yes, I would like you to start with the original equation and solve the differential equation first. The only difference between what I did and what you're going to do is what is TM in example 2? Can somebody tell me that?
5.
5 degrees, right? So at the beginning of the problem for you, you can just plug in 5 right there. If you like, of course. Does everybody have that problem written down? Okay.